The law of conservation of momentum. So we started out, after solving some basic problems, started out with some collisions using the carts and the track and the using the carts and the track and the lab quest and the motion detector. Got a couple of motion detectors on both sides to give me the data. Started out with that one. We had a couple of collisions, one of which was that perfectly inelastic, no bounce at all. Then you had the other one where, well, there's this. You kind of tap that thing and anyway, you try to tap the thing, right? You get do that, and then you get the momentum of the two, the recoil problem, and then you have the magnets. Oh, look at that! So fun. What we call the elastic collisions, where the momentum and the kinetic energy are both conserved. So start out with that. One-dimensional, because one dimension is a straight line. Then we move on. Then we move on to these. Two, well, they're kind of like pool balls. They're bocce balls, and you have two different colors. Just because, oh yeah, I guess it's for the two teams. And then you, on the floor, using the iPad and the Vernier Physics Video App, you have this one sitting there, this one comes in, and they bounce. And if you do it well, and you don't want it to be like directly in line, because you already did that here, you want them to be, this is two dimensions. You want it to come in like this, and then bounce at a pretty good angle. And then see whether or not the momentum of the ball coming in is the same size and direction as the momenta of the two balls going off at the end. And that's what you test. That's what we're doing today. Two-dimensional law of conservation of momentum and checking to see if this collision is actually elastic, like I've always been told. Camera's too close in that one. Much better perspective. Cut that video, then import it into the Video Physics app. Track the one ball. You get a y versus x versus time, x velocity versus time, y versus time, and y velocity versus time. And tracking the other ball, you get the same graphs. And what we're looking for is a before picture and an after picture with all the data on it. You could export data to a graphing app, but that's too easy. So here's a x velocity versus time, not really usable. What you want to do is find the slope of these two individual sections here. That's kind of what you have right there. You need to pick out a section, and it's about a straight line, and then find the slope of that. Slope is the rise over the run. The displacement over the time would give you the velocity. And for the iPad that runs at 30 frames per second, 8 points represent 7 intervals, or 7/30ths of a second. So find the velocity, the constant velocity, during that time interval, on the way in and on the way out. So again, you've got the before and after picture, left and right, and you want to take the graphs, not that one, but this one, and find the slope of those two individual pieces for the x velocity. So here's the before, 0.7 of a meter, 13 intervals, 1.62 meters per second, and the after for the vx, 0.632 meters per second. The y velocity, same thing. You want to find the slope for the y component of the velocity on the way in. Orange ball numbers on the diagram. Now for the other application, tracking the other ball. Find the slope of the x position versus time graph and the slope of the y position versus time graph to get the after velocity, because the before is 0, of that second ball that gets struck. Remembering that it's a real situation, that you're trying to represent this motion on the diagram, put all the velocities where they should be. So 1.62 meters per second, and then the x and y components. Then from the x and y components, you can finish the triangles with the hypotenuse and the angles. Notice the 31 degrees and the 39 degrees. You can find the mass for momentum, but it turns out that the masses are like 1 gram apart in almost 500 grams. Unimportant. So I'm going to use velocity instead of momentum because the ratios are the same. Remember that momentum is a vector. And again, remembering that I'm dealing with velocity instead of momentum because it's going to be the same ratios. I deal with the x direction first. 1.62 meters per second of momentum and 0.792 and 0.632 for that total, 1.42. And the difference is 0.2 meters per second. The original is 1.62 meters per second. 12% loss of momentum in the x direction. Now the y direction, there's nothing at the beginning, so there shouldn't be any at the end. So that 0.468 and 0.513 would ideally be exactly the same. Turns out that the percent difference is about 8%. So we've got the data, took the velocities, and found the individual momenta in the y direction, 8% difference for the y direction. In the x direction, a 12% difference. So what is that? Average of 10%. So we lose 10% momentum. Momentum is, well, it's the velocity basically. So if we lose 10% of the momentum, kinetic energy is 1/2 mv squared, and I would expect a loss of probably 20%, because you know, you take 10%, 0.9, square that, you get 0.81. And so it's about 20% that you would expect if you lose 10% of the momentum. But kinetic energy is not a vector. It's 1/2 mv squared, so I'm going to use the velocities, the 0.92, the 0.814, and the 1.62 meters per second. You can do it this way. Find the initial kinetic energy is 0.604 joules. Final kinetic energy is the sum of the two individual kinetic energies, and you get a total of 0.347 joules, which is a loss of 0.257 joules, and well, an overall loss of about, well, that's almost 43%. It's crazy. Well, do you get the same if you use the velocity instead of the momentum or the kinetic energy? Okay, 1.62 meters per second. The initial velocity squared is 2.62. And the sum of the individual velocities at the end squared, 1.51. So comparing the two, look at that. You get exactly the same percent loss, 42%. In this case, we lost more than 40% of the kinetic energy. And I think it's because when these two, partly because when these two came in, first of all, they're rolling. And we're not taking that into account. There is rolling or rotational kinetic energy. There's rolling or angular momentum. And then when they hit, they bounce off and they rotate in different directions. And you can see it in the video. There's a curve in a lot of the videos. As this thing comes in and bounces, there's a curve, and then it stabilizes and starts rolling in that straight line. So you ignore the first few points. This one, some of the videos that I've seen, significant curve as the thing spins like crazy and then establishes itself in a straight line. That friction on the floor may be the cause of the loss of the momentum, and it may be part of the cause of the loss of the kinetic energy. And then this, I don't even know how to quantify sound energy, but that's pretty loud when you have that collision. So losing some energy there, no longer all kinetic energy. And then spinning, friction on the ground, losing some energy to a little tiny bit of heat in the ball and on the ground. So overall, I kind of came to the conclusion today that, well, I was told and I've read and I've thought for a long time that pool ball collisions, billiards, when you have that collision, it's supposed to be an elastic collision, and kinetic energy and momentum are both conserved. But if I lose 40% of the kinetic energy and I only lose 10% of the momentum, I'm thinking that although better than lots of collisions with regular basketballs or bowling balls rolling down the hall, this is still not really anywhere near the molecular collisions that happen all the time in front of our eyes. Between us right now, all that little air, all those molecules are vibrating back and forth and smacking into each other at really high speeds. Those are good elastic collisions. Momentum and kinetic energy are really conserved. We may consider this to be an elastic collision for purposes of discussion, but it's not really. Maybe on an air hockey table where you have these big, massive, hard discs, suspended on a cushion of air, maybe they would be, because you wouldn't have the rotation and you wouldn't have the friction with the floor. Maybe that'd be better. But I'm pretty sure that pool balls, and I know that bocce balls, are not too good. These, however, those magnet card collisions, you take big mass, little mass, and you can get some pretty good, solid results, and kinetic energy and momentum are both conserved. So these get good data, and they do turn out to be elastic collisions. So there you go, the law of conservation of momentum in 2 dimensions. Probably not an elastic collision between these, but there you go.